All right, in this video, we are going to talk about the paired Wilcoxon signed rank test. So, for paired T procedures, the paired T test that we talked about previously, we require that the paired difference variable be approximately normal. So, we did that, and by calculating the difference variable, so whatever population 1 is minus population 2, and looking at that variable and checking the QQ plot on that if the sample size was small. And if it is approximately normally distributed, then we could use the paired t-test. If the sample size is large, then we can go ahead and proceed with the paired t-test as well. So this paired Wilcoxon signed rank test is what test you would use if you are the test that you would go to if you had a paired sample and the differences were not normally distributed. Okay, so you would next look to this Wilcoxon signed rank test. And the requirement on this, other than simple random paired sample, is that the paired difference variable has to have a symmetric distribution. So those are going to be our two assumptions for the paired Wilcoxon signed rank test: simple random paired sample and symmetric differences. And of course, this is to test to compare two population means mu1 and mu2. Okay. Everything else about this test is the same as the ones that we've done before. It's the same framework, same null hypotheses, same possible alternative hypotheses, and the same procedure and interpretations there. So we need to know how to check the assumptions. Number one, simple random paired sample. You would check the problem statement, obviously, to see if it's a paired sample. Remember, that's not independent. Where independent, any possible sample of population 1 could occur, any possible sample of population 2 could occur. So that's independent, but this has to be paired, right? So who you can pick from the second population, right, depends on who you picked in the first population. All right. So you need to check the problem statement for that and make sure that it is paired before using this. And then for symmetric differences, we're going to perform a box plot on the differences. So you'll have to calculate the differences just like we did with the paired t-test. Only here, we're not checking the QQ plot for normality. We are checking the box plot to see if it's symmetric or not. All right, let's go ahead and get right into our example here. It says the U.S. Census Bureau publishes information on the ages of married people in current population reports. A random sample of 10 married couples gives the data on ages in years shown in the second and third columns on table 10.14. The fourth column shows the pairs differences obtained by subtracting the age of each wife from that of her husband. At the 5% significance level, do the data provide sufficient evidence to conclude that the mean age of married men differs from the mean age of married women? All right, and here we're just going to go ahead and perform the Wilcoxon signed rank test since this is our first example here. Okay, so opening up R and getting started there, I'm going to go ahead and clear the screen here and save that, and then import the data. So that's read.csv. I'm going to import that into the variable df, and my data is located here. Your data probably someplace different, right? So if you're downloading this data file, again, I just kind of recommend you download it into your wherever this script is located. I've already set my working directory and all that, so just download it into your working directory. That's the simplest thing to do. But for purposes of the repository, I like to keep it separated. All right, and then I'm going to take a look at that data frame and just make sure that everything is good. So here I have population 1 is the husband data, and then wife is over here, population 2. All right, that looks good, so I'm going to turn this off, I'll comment that out so it doesn't keep popping up. And then I'm going to extract those columns. And here we don't really have any problems with NAs, but it's not a, you should always kind of keep that in mind because it can throw off your results if you're not careful. So I'm going to extract the husband column and wife column into the variables H and W. And then now it's time to check the assumptions. All right, the first assumption is simple random paired sample, and I believe it states that in the problem, right? It says a random sample of 10 married couples, right? And so it's husband and wife here, they are paired up, okay? So it's a simple random paired sample. So that's satisfied. And then next up, we need symmetric differences. So here we're going to have to calculate the differences. And so that's going to be H minus W. I'm going to store that in a variable called diffs, right? So whatever these variables are that you extract to, just subtract those. And then I want a box plot of those diffs, and then I also want to see where the mean is located. And mine is kind of scrunched up here, so I'm going to open it up, I'll make it a little larger here. And so looking at it, it doesn't look perfectly symmetric, right? This is where the median is right here, where that dark line is, and then the mean is where we put that little point. They are fairly close together, right, in there. So again, because of the small sample size, 10 observations, we can't expect this to be perfect. So, but it does look okay, in my opinion. Again, that's going to be subjective. So, but here we'll go ahead and say the distribution, the differences look symmetric, or have a symmetric distribution here. So the assumptions are satisfied. Okay, so next up we need to formulate the null and alternative hypothesis. So the null is going to be mu1 equals mu2. And the alternative hypothesis, the statement of the problem says, do the data provide sufficient evidence to conclude that the mean age of married men differs from the mean age of married women? So it's not equal to on the alternative hypothesis. And alpha equals 0.05, I believe. Yep. All right, next up we need to perform the tests. And we're going to use the same one that we used for both the Wilcoxon signed rank test for one population mean and also the Mann-Whitney, which is wilcox.test. And H is our population 1, W is our population 2. Our alternative hypothesis is two-sided. And then this one is the key, right, for the paired, is that you have to set paired equal to true here, okay? Let's see. That's weird. Let's because this is really weird. I haven't encountered this before. Let's save that. No. Okay, the trouble was up here. Okay, so here, no, that's fine. Let me try pulling it all back on one line. Yeah, I don't know what that was. Something about how the line split there. Let me try it again. Yeah. There was some weird thing where maybe I had like an extra space in there or something caused the issue there. Okay, so looking at my test statistic, I get 46.5. If you remember back with the Mann-Whitney one, it was reporting that W statistic, the Wilcoxon one, instead of the Mann-Whitney, and we had to make an adjustment there. That was for independent samples, but here we do not have to do that. So this one is the same one that will be reported in our textbook. So you don't have to check that. That should come out to be exactly the same. The p-value here was 0.0588, right? And so the results of our test, right, the p-value is greater than or equal to alpha, right? So we fail to reject the null hypothesis. And the interpretation, the data do not provide sufficient evidence to conclude that. And then the alternative hypothesis stated in the context of the problem. And that was that the mean age of married men differs from the mean age of married women. All right, and that is it on this one.